So example 2, solve the d for x squared dy dx is equal to 3x squared plus y squared. Now, this is another first order homogeneous differential equation. This is of degree 2, degree 2, degree 2. But if we try to separate the variables here, we may not be able. So, may not be able to do that easily. So the only thing that we can be able to do, if all the terms are of the same degree, we can use the procedure of solving first order homogeneous differential equation. So in our solution, we say dy dx will be equal to 3x squared plus y squared all over 4x squared. From here we let y to be equal to bx. This implies what? Dy dx is equal to v plus x dv dx plus x dv dx plus x dv dx. It's equal to v plus x dv dx. So when we substitute in this, what do we get? It will be v plus x dv dx being equal to 3x squared plus v squared x squared all over 4x squared. So v plus x dv dx will be equal to 3 plus v squared all over 4. This implies x dv dx will be equal to 3 plus v squared all over 4 minus v. So dv x dv dx will be equal to x dv dx will be equal to v squared minus 4v plus 3 all over 4. So this implies now we can separate the variables 4 all over v squared minus 4v plus 3 dv is equals to dx all over x. We have managed to separate the variables. Now we can be able to integrate both sides so that we can get our solution. So the integral of 4 all over v squared minus 4v plus 3 dv will be equal to the integral of 1 all over x dx. Now the integral where we have the variable b, the derivative of the denominator is 2v minus 4. Here we don't have 2, there is no v up here. So we cannot follow such a method of integration. Now we check. Our denominator is a quadratic term. We check whether we can be able to factorize that particular quadratic term. In this case, as it is seen, we can be able. So that's what we do first. So this is the integral of 4 all over v minus 3 into v minus 1 dv will be equal to 1 all over x dx will be equal to 1 all over x dx. Now we have something which has got factors in the denominator. Such a fraction can then be split first into partial fraction. Now we can branch a bit and say, but for all over v minus 3 into v minus 1 is equals to what? This one will be equivalent to maybe a constant a all over v minus 3 plus a constant b all over v minus 1. This implies what? A into v minus 3 plus b into v minus 1. This is what is equals to 4. If we prepare the numerator of this side, that's what it will read. And this numerator should be equated to that numerator because the LCM of these two fractions will still be this particular denominator. So we equate. When we equate like that, we should now find the values of A and B. So many methods of getting values of A and B there, but we can use the simplest method of doing so. So we can say put V is equals to 3 in this expression. When we put V is equal to 3, B will be into 3 minus 1 is equals to 4. So our B will be equal to 2. B will be equal to 2. Put V is equals to 1. And V is equals to 1. What do we get? A and 2. Negative 2. And A into equal to negative 2 will be equal to 4. So we say now A will be equal to negative 2. A will be equal to negative 2. Now after getting that, we say this implies what? Our integral now becomes what? A negative 2. B positive 2. So 2 all over V minus 1 minus 2 all over V minus V minus 3 dV is equals to the integral of 1 all over x dx. Let's have that integral sign. So from this, when you integrate 2 all over this, you get 2 ln of v minus 1 minus 2, because the derivative of this is 1. 1 is here. So 2 ln of v minus 3 is equals to now, the integral of this becomes plus the constant, it will be integral ln of kx. Or integral of ax. It will be ln of ax, that is. ln of ax. This implies what? ln of v minus 1 all over v minus 3 squared, because of these two that we have here, and because by laws of logarithm, if you combine this is what you get. Will be equal to ln of a times x by laws of logarithm. So this implies v minus 1 all over v minus 3. When it is squared, is equals to what? Ax. Is equals to ax. Now from here, maybe we can remove this power 2 to bring us power 1. We can remove power 2 to bring us. So we take square roots both sides. When we take square roots both sides, I'll get that one as So we say this implies v minus 1 all over v minus 3 is equals to a power a half, x power a half. We are taking square root both sides. So from this now, we say this implies what? We are replacing for the value of v, y all over x minus 1, all over y all over x minus 3 is equals to a power half. A power half, which we can call it b, another constant, arbitrary constant. X power half is just x power a half. Now this implies what? This is y minus x all over y minus 3x is equals to b x power a half. Bx power a half. So the solution we can write as, the solution now we can write as, we can have this one x power half remaining this way. We take this one this side, so we can say 1 all over b. 1 all over b is equal to x power half into y minus 3x all over y minus x. Therefore, the solution to the dE, can be written as root x into y minus 3x all over y minus x. This one being equal to a constant c. In our type 3, it is first order linear differential equation, and it takes the form dy dx plus py is equal to q. This is a case where dy dx is of first degree. Y is also raised to power 1. Hence the name first order linear differential equation. Now, if it is in this format where p and q are just functions of x, we can solve it as a first order linear differential equation, which requires an integrating factor to enable you to solve. Now, the integrating factor that is to be used, IF, will be equal to, the integrating factor will be given this. To solve the above equation. An integrating factor is required. Integrating factor is required. Is required. That is IF, which is the integrating factor, will be the integral, will be equal to e power the integral of p dx, the exponential raised to a power of integral of p dx. This implies now we multiply the whole equation by the integrating factor. The integral p dx dy dx plus p e power the integral of p dx y will be equal to k e power the integral of p dx. No, this is a plus, not equal to. That is a plus. We are taking it from this equation. That is a plus. Now, the whole of this side becomes now the integral of two terms which are being multiplied together. So, the whole of this side, if we clear it nicely, it just becomes y multiplying the exponential p dx will just be equal to k a or the integral of p dx. So this will be d dx, the whole of this side, d dx of that. Now, if we differentiate this, we get from here up to there. So d dx of this gives us that. And it is equal to this other one. So from here, we can now say d. We multiply both sides by dx. Y e power the integral of p dx will be equal to k e power the integral of p dx dx. Now, if we integrate both sides, after separating, these are all in excess, and this is d of some combination of terms here. And we say the integral of now d y e power the integral of p dx will be equal to the integral of k e power the integral of p dx dx. So this one will give us the solution to the first order linear differential equation. So the integral of the something, the answer is that something. Like the integral of dp, the answer is p. The integral of dy, the answer is y. So the integral of d of this something that we have here, that is y multiplying the integrating factor, p dx, will be equal to the integral of q e power the integral of p dx dx. Therefore, the solution to the first order dE, the solution to the first order linear dE, therefore the solution to the first order, linear dE is given by y, is given by y multiplying the integrating factor, which will be equal to the integral of k multiplying the integrating factor, then dx. And that's how we'll be solving our first order linear differential equations. So in our example 1, solve the dy dx minus 2 all over xy is equal to x power 4. dy dx is to power 1, y is to power 1. Other things which are remaining are functions of x. Hence, it is now a first order linear differential equation. So we say in our solution, we say this is in the form, this is in the form, dy dx plus py is equals to q. In our case, this implies our p is equal to minus 2 all over x. And q is equals to x power 4. Q is equals to x power 4. We need the integral of p dx. Integral of p dx will be the integral of minus 2 all over x dx, which will be equal to minus 2 ln of x, which is equal to ln of x raised to power minus 2, which is equal to ln of 1 all over x squared. 1 all over x squared. The integrating factor will be equal to exponential, the integral of p dx, which is equals to exponential ln of 1 all over x squared. From this, e power ln of that. So if you have an exponential, e raised to a power where the coefficient of ln here is 1. So we say e power ln of anything that you see, the answer is that something. So e power ln of 1 all over x squared, the answer is 1 all over x squared. 1 all over x squared. And that will now be our integrating factor. But the solution to the dE, is given by y now multiplying the integrating factor 1 all over x squared, which would be equal to the integral of q. Our q was x power 4. Now multiplying integrating factor 1 over x squared, then dx. This implies what? Y all over x squared is equals to the integral of x squared dx. Integral of x squared dx, which simplifies to y all over x squared is equals to x cubed all over 3 plus a constant of integration, which you can call k or c. Therefore, y is equals to a third x power 5 plus kx squared. And that is the general solution to that differential equation. That's the general solution to that differential equation. So in our example 2, solve the d sine x dy dx plus y cos x is equal to sine x cos to power 4x. Given that when x is 0, y is equal to 0. In our solution, dy dx is raised to power 1. Y is also to power 1. And there is no other function involving y. So y power 1 dy dx is to power 1, so it is a first order linear differential equation. Other terms remaining are functions of x. So it is a first order linear differential equation. So in our solution, we should put it in the form dy dx plus py is equals to q. So this one will be equal to sine x cos to power 4x all over sine x. This simplifies to dy dx plus y cos x all over sine x is equal to cos to power 4x. Is equal to cos to power 4x. So this implies what? Our p now is cos x all over sine x. So p is equals to this. The integral of p dx will be equal to the integral of cos x all over sine x dx, which will be equal to ln of sine x. In such an integral where we are getting the something to use in integrating factor, we don't add a constant k. We don't add a constant of integration because it's already contained in our derivation when we are deriving formula for solving first order linear differential equation. So that's the integral of p dx. Integrating factor will be equal to e power ln of sine x, which is just equal to what? Sine x. Which is just equal to sine x. Therefore, the solution to the dE is given by y now multiplying the integrating factor, which is sine x, is equal to the integral of k. K is cos raised to power 4x. Now multiplying the integrating factor, which is sine x dx. So y multiplying sine x will be equal to this is cos to power 4. Now, derivative of cos is negative sign. So we can say we need this one to read sine x so that we can be able to integrate easily. So this one will be minus there. Then we say cos to power 4x multiplying negative sine x dx. So this minus, when you multiply with that minus, you get a positive. But you are inputting it here so that it acts as a derivative of cos x, which is in a bracket here, raised to power 4. When we have such, we need just to raise this power by 1. So we raise it by 1, so it will be cos to power 5x all over the same value 5. Now plus a constant of integration, which we can say k. That is why sine x is equal to that. This implies y will be equal to what? Minus 1 over 5 cos to power 5x sine x plus over sine x plus k all over sine x. Now this is the general solution to that particular differential equation, which can be simplified as y is equals to minus 1 all over 5. We have cos x all over sine x is tan x. So we can have tan x. Then we remain with cos to power 4x. plus k cosec x. Plus k cosec x. X is equals to pi all over 4. When x is equals to pi all over 4, y is equals to 3. Y is equals to 3. This implies 3 is equals to minus 1 over 5 tan pi all over 4 cos pi all over 4 raised to power 4 raised to power 4 plus k cosec pi all over 4. So 3 is equal to this. Tan pi all over 4 is 1. Cos pi all over 4 is 1 all over root 2. Raised to power 4 is a quarter. What raised to power 4 is 4. 1 all over root 2 raised to power 4 is a quarter. So this is minus 1 all over 20 plus root 2k. So this implies k will be equal to 61 all over 20 root 2. 61 all over 20 all over root 2. Therefore, particular solution is given by y is equals to negative 1 all over 5 tan x cos to power 4x plus 61 all over 20 root 2. 61 all over 20 root 2 cosec x. That's that. Now after finishing this, we are through with first order linear differential equation. Our next lesson will be looking at first order exact differential equation. First order exact differential equation.